All right, so picture this. You're in the lab first thing in the morning and, you got samples coming in, you're running tests, maybe even getting ready for, one of those manual differentials. But
Yeah.
um, have you ever just, like, taken a second to actually think about what's in those tubes? You know?
Oh, yeah.
It's pretty wild when you consider it. Like,
It's pretty
it's
amazing.
not just some, uniform red liquid.
Oh,
It's
yeah, absolutely.
billions of cells all doing their thing.
There's a whole world in there, right?
Exactly. A whole world. And for us as medical laboratory scientists, we gotta know this stuff inside and out.
Right.
Red cells, white cells, platelets, the whole crew.
Yeah. That's the foundation, isn't it?
It really is. I
Yeah.
mean, because without that solid understanding, how can we trust our results? How can we make those critical interpretations?
Exactly. It all comes back to those basics.
Exactly.
Yeah.
So that's exactly what we're diving into today. A real deep dive into hematology.
Mm.
Our mission here is to kind of like, put it all together, get that clear understanding of those three main players,
Mm-hmm.
erythrocytes, leukocytes, and thrombocytes,
Yeah, the big three.
the big three,
Uh-huh.
how they're made, what they do,
Mm-hmm.
and how they're, eventually taken out of circulation.
Yep. Their whole life cycle.
Exactly.
Yeah.
And we've got some awesome sources, really focused on hematology that paint a really detailed picture of these essential cell lines.
Yeah. We're going to get into the nitty gritty.
We are.
Yeah.
We're getting into the nitty gritty. So think of this as your go-to guide for the essentials.
Okay. I like it.
We're going to pull out the highlights from from their birth to their function and then, to the end of the line.
Yeah.
And really emphasize, why this matters so much
Oh.
for what we do every day in the lab.
Yeah, because it's not just theoretical, right? This is
Not just theoretical.
directly applicable to our work.
Exactly, because ultimately those numbers, those morphologies we're looking at,
Yeah.
those are a reflection of, what's happening at that really basic biological level.
It all connects.
It all connects.
Yeah.
So let's start, I think, with the, kind of the stars of the show, the red blood cells, the erythrocytes, those oxygen carriers.
Yeah.
Where does their story even begin?
So red blood cell production, erythropoiesis, it's a tightly controlled process. And for adults, it mainly happens in the bone marrow.
Okay.
And that's important to remember, right? Because if anything affects the bone marrow, their production is going to take a hit.
That makes sense.
But the body is pretty smart. It has backup plans.
Oh, really?
So in some cases, red blood cell production can actually happen outside of the bone marrow.
Wow.
It's called extramedullary hematopoiesis.
Pretty cool, huh?
That is cool. I had no idea. So, okay, bone marrow is the main factory. What's the production look like? What are the steps, from, just a basic cell to a mature red blood cell? All right, so it's a pretty fascinating sequence. It starts with a hematopoietic stem cell, or HSC.
Okay.
Think of it as the ultimate blank slate.
Right.
From there, it becomes a common myeloid progenitor, or CMP.
Got it.
And that's where things split off. Different lineages come from that CMP.
Okay.
For red blood cells, we then get the burst-forming unit erythroid, BFUE, and then the colony-forming unit erythroid, CFUE.
Okay.
These guys are committed to becoming red blood cells.
Okay.
And then they go through several stages, getting more and more red blood cell-like as they go.
Mm-hmm.
Pronormoblast, basophilic normoblast, polychromatic normoblast, and finally the orthochromic normoblast.
Okay, I'm trying to picture these as you're saying them. It's like a little animation in my head.
And there's one really important step here.
Mm-hmm.
At the orthochromic normoblast stage, the nucleus gets kicked out.
Oh, wow. So it just like gets rid of it.
Gone.
Yep.
What's left is a reticulocyte.
Okay.
It's a young red blood cell, still has a bit of RNA hanging around, but it's almost there.
Almost there.
Mm-hmm.
And then from there, it becomes that, fully functional erythrocyte that's, coursing through our veins.
Exactly. Ready to do its job.
Wow. It's like a whole, coming of age story for a cell.
It really is.
So, okay, we've got this whole, production line happening, but what's the signal? What tells the bone marrow, hey, we need more red blood cells, or hey, slow down?
So the main signal is erythropoietin, or EPO.
Yeah.
This hormone mainly comes from the kidney, and it's released when oxygen levels in the tissues get low.
Okay.
So basically, the body says, hey, I'm not getting enough oxygen. Kidneys kick into gear, pump out EPO, and that EPO goes straight to the bone marrow and says, hey, we need more red blood cells stat.
That's pretty cool.
And this is really important for us in the lab, right?
Well, how so?
Think about patients with chronic kidney disease. Their kidneys aren't working as well, so they often can't make enough EPO.
Okay.
And that leads to anemia.
Right.
It's a direct result of that disrupted regulation. Now, EPO isn't the only thing needed, of course. We got to have those building blocks, iron, vitamin B12, folate.
Right.
And then there's hemoglobin synthesis. That's where the oxygen-carrying molecule is actually made.
Oh, right. Hemoglobin. That's a big one.
Huge. And it involves making both the heme part, which has the iron, and the protein part called globin.
Okay, so how do we actually assess, in the lab if this whole red blood cell production system is working the way it should? What are the tests that kind of, give us that insight?
We've got a good arsenal. The CBC, of course, is essential. It gives us hemoglobin, hematocrit, red blood cell count, and the MCV.
Mean corpuscular volume.
Right. It tells us how big the red blood cells are on average.
Okay.
And then the reticulocyte count, that's a really important one because it tells us how active the bone marrow has been recently, pumping out new red cells.
So it's like a measure of, recent production.
Exactly.
Yeah.
Then we've got the peripheral blood smear, where we can actually look at those red blood cells, see their shape, their size, any weird morphology.
You can actually see them.
Yeah, we get a visual.
That's all.
And then iron studies. That gives us a good idea of the body's iron stores.
Okay.
Serum iron, TCC, transferrin, saturation, ferritin, the whole panel.
Right.
And sometimes we might even measure EPO levels directly.
Okay.
And if we're really concerned about the bone marrow itself,
Yeah.
we might need to do a bone marrow exam to get a closer look at those developing red blood cells.
I'll see that we can see the factory floor, so to speak.
Exactly.
Wow. Okay, so we've covered how they're made and, kind of how we check if that process is going. Okay, but what about once those erythrocytes are out there, circulating? What's their main gig? What do they do?
Their main job is pretty straightforward. They transport oxygen from the lungs to the tissues, and they bring back carbon dioxide, that waste product from metabolism, back to the lungs to be exhaled.
So they're like the delivery service.
Exactly. They're the body's oxygen and CO2 delivery system,
I like it.
keeping things running smoothly.
Okay, and a big part of this whole delivery system is hemoglobin, right? That molecule inside the red blood cell that actually carries the oxygen. So can you give us like a crash course on hemoglobin?
Right.
What's it made of? How does it actually grab onto those oxygen molecules and then let them go?
Sure. So each hemoglobin molecule has 4 subunits.
Okay.
In the most common type we see in adults, HbA,
HPA.
each subunit has a globin chain, 2 alpha and 2 beta, and a heme molecule.
Okay.
Now, in the center of each heme, you've got an iron atom. It's in the ferrous state Ft2+.
Okay.
And that's where the oxygen binds.
The iron is like the little hook that grabs the oxygen.
Exactly. And each hemoglobin molecule can actually carry up to 4 oxygen molecules.
Wow, that's a lot.
It is. And the way they bind is cooperative.
Cooperative. What does that mean?
So basically, once one oxygen molecule latches on, it makes it easier for the others to bind as well.
Oh, interesting. So it's like a team effort.
Kind of, yeah. There's a curve that shows this relationship between oxygen pressure and how saturated the hemoglobin is. It's called the oxygen dissociation curve. Okay. And the P50 value, that's the oxygen pressure where hemoglobin is 50% saturated.
Okay.
And things like pH, carbon dioxide levels, temperature, even 2,3-DPG can shift this curve. And that affects how tightly hemoglobin holds on to oxygen.
So it's like, different conditions can make hemoglobin, either more eager to give up the oxygen or
exactly.
Hold on to it a bit tighter.
Right. And that's why blood gas analysis is so important clinically. It helps us understand what's going on with oxygen delivery in different situations.
Makes sense.
Yeah.
So you mentioned HbA. What about some of the other hemoglobin variants we might see, when we're looking at results?
So HbA is the most common one, but we also see HbA2.
HbA2.
That's alpha 2 delta 2. It's around in smaller amounts. Then there's HbF.
HbF.
That's the main one in fetuses and newborns. It actually has a higher affinity for oxygen, which is super important when you're, growing in the womb.
So it's like it's grabbing onto that oxygen even more tightly.
Exactly. Giving the fetus what it needs.
That's amazing. And what about the abnormal variants?
So there are a few. For example, HbS.
HbS. That's the one you see in sickle cell disease. Right. It has just one tiny amino acid difference.
Just one.
Yep. But it causes the hemoglobin to polymerize when oxygen is low, and that leads to the sickling of the red blood cells.
Right.
Then you've got HBC.
HBC.
That one can cause a mild hemolytic anemia.
Okay.
We also have methemoglobin.
Prostanoglobin.
That one's got iron in the ferric state, F3+,
Okay.
and that can't bind oxygen.
So it's like a non-functional hemoglobin.
Pretty much.
Okay.
And then there's carboxyhemoglobin.
Carboxyhemoglobin?
That forms when carbon monoxide binds to hemoglobin.
Oh, right, carbon monoxide.
And carbon monoxide actually has a way higher affinity for hemoglobin than oxygen does.
Oh, wow.
So it basically kicks oxygen out, and that really reduces the blood's oxygen carrying capacity.
So it's like carbon monoxide's a bully?
Kind of, yeah.
Yeah.
It hogs all the space.
That makes sense. And, understanding these different variants, it seems like that's really important for interpreting tests like hemoglobin electrophoresis.
Absolutely. It helps us make sense of the results. So it's not just about what's inside the red blood cell, right? Like
Yeah.
the cell itself has to be, you know, structurally sound to do its job and, just to survive out
Yeah.
there in the circulation.
Yeah, it's got to be built, right?
So tell us about the red blood cell membrane. Like, what's it made of? How does it, stay in one piece?
So the red blood cell membrane, it's a pretty amazing structure. It's a lipid bilayer, but it's got this whole cytoskeleton made of proteins.
Okay.
Spectrin and ankyrin are two of the big ones.
Okay.
And this framework gives it that flexibility, so it can squeeze through those tiny capillaries.
Like those tiny little blood vessels.
Exactly. It's got to be bendy. And then you've got these transmembrane proteins.
Okay.
Band 3 is one. It's involved in swapping chloride and bicarbonate ions.
Okay.
And glycophorin A, that helps give the cell a negative charge on its surface so the red blood cells don't clump together.
So it's like it's keeping them from getting too friendly.
Yeah, exactly. Keeping them separate.
I like it. And what happens if there are problems with these membrane proteins? Like, what are some of the consequences?
So you can get conditions like hereditary spherocytosis or hereditary elliptocytosis.
Okay.
And in the red blood cells, they're misshapen.
Okay.
And that makes them less flexible and they don't live as long.
So their shape really matters.
It really does. It affects their whole lifespan and how well they function.
And these cells, even though they don't have a nucleus, they still need energy, right? Like to keep their shape, to do their job.
Yeah, they got to keep the lights on.
So what are the main metabolic pathways happening inside a mature red blood cell?
Well, they might not have a nucleus or mitochondria, but they've still got some important metabolic pathways going on.
Okay.
Glycolysis is one. It makes ATP, which is the cell's energy currency.
Right.
And that's needed to keep the cell in the right shape and keep the membrane strong.
Okay.
Then there's the pentose phosphate pathway.
Pentose phosphate pathway?
It makes NADPH, which protects the cell from oxidative damage.
Okay.
And the methemoglobin reductase pathway.
Methemoglobin reductase.
That one makes sure the iron in hemoglobin stays in that ferrous state, Fe2 plus.
Right, the functional state.
Exactly. And then there's the Rappaport Lubering shunt.
Rapport lubricant shunt.
Try saying that 3 times fast.
I'm not even going to try.
It makes 2,3-DPG, which we talked about earlier, remember? It regulates how tightly hemoglobin holds on to oxygen.
Oh, right.
Now, if any of the key enzymes in these pathways are deficient,
Yes.
like pyruvate kinase or G6PD,
G6PD?
red blood cell metabolism can get messed up, and that can lead to hemolytic anemia.
So these pathways are really important.
They are. And we see G6PD deficiency testing pretty often in the lab when we're trying to figure out what's causing an anemia.
So we talked about oxygen transport, but earlier you also mentioned carbon dioxide transport.
Yeah.
Like, how do red blood cells actually help get rid of CO2?
Red blood cells have a few tricks up their sleeves when it comes to CO2 transport.
Okay, and let's say.
A small amount of CO2 just dissolves directly in the plasma.
Okay.
Another chunk binds to hemoglobin to form carbaminohemoglobin.
Carbaminohemoglobin?
But the majority of CO2 is actually transported as bicarbonate ions.
Like carbon.
Yep. Inside the red blood cell, there's an enzyme called carbonic anhydrase.
Okay.
And it quickly converts CO2 and water into carbonic acid.
Okay.
Then that carbonic acid breaks down into hydrogen ions and bicarbonate ions.
Okay.
And to keep things electrically neutral,
Right.
the bicarbonate ions are swapped for chloride ions across the red blood cell membrane.
Okay.
That's called the chloride shift.
Chloride shift.
And it all happens thanks to that band 3 protein we talked about earlier.
It's just like a whole coordinated exchange.
Exactly. It's a beautifully balanced system.
It is.
Yeah.
So they're not just delivering oxygen. They're actively involved in getting rid of CO2.
Yeah.
That's pretty efficient.
It's a two-way street.
So after about 120 days of, doing all this work,
Yeah, they put in their time.
what happens to these red blood cells? Like,
Yeah.
how are they retired?
Yeah.
How do they get out of the circulation?
That brings us to erythrocyte destruction or hemolysis.
Hemolysis.
It's the process of getting rid of old or damaged red blood cells.
Okay.
And it happens mainly in two ways: extravascular hemolysis and intravascular hemolysis.
So two main pathways.
Yep. Let's start with extravascular hemolysis. That's the main one.
Okay. So where does that happen?
It mostly happens inside the cells of the mononuclear phagocyte system, or MPS.
Okay, yes.
Mostly in the spleen, but also the liver and bone marrow.
Okay.
As red blood cells get older, they start to change.
How so?
They get less flexible, their surface proteins get altered,
Okay.
and these changes are basically a signal to macrophages saying, hey, I'm ready to be taken out.
It's like they're putting up a little flag.
Exactly. And those macrophages recognize the signal, and they gobble up the old or damaged red blood cells through phagocytosis.
The macrophages are like the cleanup crew.
Exactly. Keeping things tidy.
Okay, so the red blood cells inside the macrophage. Now what?
Now it's time to break it down.
Okay.
Hemoglobin gets broken down. The globin chains are turned back into amino acids, which the body can use to make new proteins.
So it's like recycling.
Exactly. Nothing goes to waste.
I like it.
Iron is released from the heme, and it can either be stored in the macrophage as ferritin or hemosiderin,
Okay.
or it can be sent back to the bone marrow by transferrin to make new red blood cells.
So the iron can be reused.
Yep. And then there's the rest of the heme that gets turned into biliverdin.
Biliverdin.
Then to bilirubin. This is unconjugated bilirubin.
Unconjugated.
It goes into the plasma, binds to albumin, and travels to the liver to be conjugated.
Okay.
Conjugation makes it water-soluble, so it can be excreted in bile.
Gotcha. Now, you mentioned the spleen before. What's its role in all of this?
So the spleen, it does this cool thing called pitting.
Pitting.
It can actually remove inclusions or damaged parts from red blood cells without destroying the whole cell.
Wow, so it's like a repair shop.
Yeah, like a little tune-up. And then the red blood cell can keep circulating.
That's so cool.
Now, this is different from culling,
Culling.
with the whole red blood cell is removed because it's just too old or too damaged.
So pitting is like a second chance.
Exactly, giving them a bit more time.
Okay, what about intravascular hemolysis? When does that happen?
So intravascular hemolysis, that happens inside the blood vessels themselves.
Oh, okay.
And this can be triggered by a few different things.
Like what?
Mechanical trauma, like you see in microangiopathic hemolytic anemias,
Okay.
complement activation infections, or even exposure to certain toxins.
So a lot of different things can cause it.
Right. And when red blood cells rupture inside the blood vessels,
Yeah.
all that hemoglobin spills out into the plasma.
Okay.
And this free hemoglobin, it quickly binds to haptoglobin.
Haptoglobin.
It's a plasma protein,
Okay.
and then that hemoglobin-haptoglobin complex is cleared out by the liver.
Okay, so the liver is like the detox center.
Exactly.
Yeah.
Getting rid of that free hemoglobin.
What happens if there's just way too much free hemoglobin? Like if it overwhelms the haptoglobin, what happens then?
So when haptoglobin gets saturated,
Okay.
the free hemoglobin can be oxidized to methemoglobin,
Methemoglobin.
and the heme part can detach and bind to another protein called hemopexin. And that hemopexin complex is also taken up by the liver,
Right.
but some free hemoglobin can also get through the kidneys.
Oh, no.
Yeah, some of it gets reabsorbed by the renal tubules.
Okay.
But if there's just too much, it spills out into the urine. That's called hemoglobinuria.
Hemoglobinuria.
And the iron that's released during this whole process, it can build up in the kidney tubules as hemosiderin.
Yeah.
And that can also show up in the urine.
So increased red blood cell destruction can really have some noticeable effects.
Definitely, clinically and in the lab.
So what are some of the signs we look for in the lab that might suggest hemolysis is happening?
So if there's increased hemolysis, you might see anemia,
Okay.
jaundice from the bilirubin buildup,
Okay.
and maybe even an enlarged spleen because it's working overtime to clear out those damaged cells.
Working hard.
And with intravascular hemolysis,
Yeah.
we might see hemoglobinuria and hemosideruria in the urine.
Yep.
LDH lactate dehydrogenase.
Okay.
That's an enzyme that gets released from damaged cells, and that's often elevated. Aptoglobin, that's usually decreased because it's all used up binding to that free hemoglobin.
Right.
And on the blood smear, we
Right.
might see schistocytes. Those are fragmented red blood cells, a sign of mechanical damage.
Okay.
Or spherocytes, which are often seen with extravascular hemolysis.
Okay.
And the reticulocyte count, that's usually high because the bone marrow is trying to catch up and replace those lost red blood cells.
This is trying to compensate.
Exactly.
Right.
And we'll often see an increase in indirect or unconjugated bilirubin as well.
Right.
And then there are specific tests like the DAT, direct antiglobulin test, the osmotic fragility test, and assays for enzymes like G6PD.
Right, G6PD.
Those can help us figure out why those red blood cells are being destroyed.
So there are a lot of clues we could look for.
There are. We just got to know what to look for.
Well, that was a really incredible overview of the erythrocytes' journey
It's quite a journey.
from their start in the bone marrow to their, critical role in gas transport, and then, finally to being recycled.
Yeah.
It's pretty amazing how much goes on in these cells that, we might think are simple, but
They're little powerhouses.
they really are.